2006, researcher Tom Hamill introduced us to the revolutionary idea of a reforecast, a retrospective forecast based on past weather conditions, but using a current weather model. Reforecasts are important, especially for extreme weather phenomena, because they can detect systematic and spatial biases that past forecasts may not have been able to catch. Today, my team has developed the 32-year West Wharf reforecast, which has been crucial in identifying extrema known as atmospheric rivers, or ARs. These atmospheric rivers, or these rivers in the sky, are essentially concentrated streams of atmospheric water vapor that rise up from the tropics and deliver heavy rainfall to higher latitudes. And while they are responsible for a majority of the beneficial rainfall brought to the West Coast, they can also lead to such unexpected disasters as the 2017 Oroville Dam crisis, mudslides, and overall 1.1 billion in flooding damages annually. So clearly, ARs are a tricky weather prediction problem for us. And what makes it even harder is they can occur in a variety of different backgrounds. So what we want to do is discern whether any of those backgrounds exhibit higher or lower predictive skill. The way we can start to do that is by running thousands of atmospheric river reforecasts through a neural network classification system known as the Self-Organizing Map, or the SOM. The SOM essentially works by training on a single variable, such as our moisture term shaded down here, the integrated vapor transport, or the IVT, and then from there, iteratively compositing like cases into similar nodes, or similar categories, represented by each of these boxes here. Unfortunately, initial efforts to train on just the IVT failed to show significant differences in the patterns. So we thought, why not let the SOM do what it does best and elucidate those error patterns for us by training on the error itself, or the difference between the reforecast and the verification data set. Once we did that, the SOM was able to elucidate two main error patterns, one relating to AR translation speed, or the forecast either being too slow or too fast, and one relating to AR intensity, or the AR either being too weak or too intense. Also note that I've contoured the height patterns here, which shows the general sense of the winds. But of special importance to us are the cases where the ARs are too weak, because this often pinpoints to some sort of heating or microphysics scheme deficiency, which is something we can go back and fix in the model, rather than if it was just an initial condition error that we couldn't address. An example of the AR being too weak was observed in this February 1987 case, where, as you might notice, the predicted maximum moisture was underestimated by more than half of what was actually observed. So by training on the error, we are taking a first step toward improving atmospheric river forecasts and avoiding future flooding disasters.